Hello everyone, and welcome back to another calculus video. In this video, we are going to talk about other integration techniques, and we're really going to focus on integration using tables, and then I'm going to show you how to use some technology to help you integrate some things. But we do have to be careful with technology, especially if you're using AI. So when I talk about integration with tables, I'm talking about a list of tables that have various integration formulas on it. And all of these can be derived in some other process. Like for instance, this one, if we wanted to derive where it came from, notice u is our variable. The degree of the top is the same as the degree of the bottom, so we would do long division. And then we would integrate the quotient plus remainder over divisor, and that's where this guy would come from. So we could derive where these are coming from. Same here, this would be a partial fraction decomposition. But if you have something in this form, a plus bu, and you don't know what else to do, tables may be a great place to start. Maybe we could integrate using one of these formulas here. So here, like I said, u is the variable and a and b are constants. So the format for the um, antiderivative will come from identifying all those different pieces. We have formulas that involve a quadratic, a plus bu plus cu squared. We have some that involve square roots. And this section is really about being able to use those different techniques. So let's look at a few examples. Let's look at this first one. We have dx over x square root x minus 1, and we want to integrate using the tables. So I'm going to reorder everything here so that we can see both the tables and the problem we're looking at. So we're trying to find a formula that matches this setup. So to me, it looks like I may be able to use number 17 if we were to rewrite this a little bit. So let's think about rewriting this, that radicand, as -1 plus x. So I'm kind of got my eye on number 17 here. So my u is x, and notice my a value would be negative, because a in this case would be a -1, and my b would be the number in front of x, which would be 1, and then u is just x in this case. So we don't have to really do a u substitution. So I'm following this format here. So it's going to be equal to 2 over square root of negative a, my a is -1, arctan of the square root of a plus bu. So a plus bu over negative a, and then we're going to have plus c. So I'm going to simplify this. This is a positive 1, square root of 1 is 1, so this is 2 arctan. That denominator is 1 also, so we could rewrite this as -1 plus x, or x minus 1 plus c. So let's look at the next one. We have x square root x to the 4th minus 9. So we're trying to figure out what fit we're using. So we're looking for one of the formulas that we can use. So what if we were to think about this as an x squared minus 3 squared dx? Let's see if we can find some kind of formula that will match this. I'm looking maybe for an a squared minus b squared under a radical. So an a squared minus b squared. Maybe this guy. So we're thinking about maybe number 26. Let's see if we can force that fit. So I'm going to rewrite again. This is now x squared squared minus 3 squared. And I'm going to put that x dx here. So we're thinking about number 26. I'm going to think about a u substitution. So we're going to let u be x squared. So du is 2x dx. So we can see how that x is going to get absorbed inside of that du. But we need a 2, and we're going to compensate with a 1/2 here. So let's do that rewrite step. So when we rewrite this, it's going to be 1/2 integral square root is going to be u squared minus 3 squared dx, because remember all of this is getting absorbed inside of du. And now we can see how we can fit that formula really easily. So we're using the u squared minus a squared, so we're using that bottom sign there, which means we got to continue to use the bottom signs here, here, and here. So when we integrate, we've got that 1/2 that we pulled out. Well, we didn't pull it out. It came from the du times. We're going to plug in here. So we're going to have a 1/2. Now that 1/2 comes from the formula. That 1/2 out here actually comes from the compensation for finding the 2 as part of the du, multiplying that 2 in. So it's going to be u square root u squared minus a squared minus, because again, we're following that bottom sign here, a squared, which is 3 squared, ln of absolute value of u plus square root u squared minus a squared, and then plus c. So now we're going to do a substitution, and I'm going to clean this up at the same time. Got to be careful. Notice that parentheses around here. We're going to make sure we have that parentheses around here also. So that 1/2 times that 1/2 will be a 1/4 times all that stuff inside that inner parentheses when I substitute back in for my u. So this is going to be u, which is x squared, square root of x squared squared, which is x to the 4th minus 9. Minus 9 ln absolute value of x squared plus square root, and this is going to be an x to the 4th minus 9 also. And then we're going to have a plus c. So there's my antiderivative for that one. Let's look at another one. Let's look at number 3. So we have x over 1 plus e to the negative x squared. So we're looking for something maybe that has an e in it. Let's scroll through our tables and see if we see anything. What if we were to compare to maybe number 84? Let's do a u substitution. Let's let u be negative x squared. So du would be minus 2x dx. So you can see how that 2 is going to get, that x in the numerator is going to get absorbed inside of our du, but we do need a negative 2 here, compensate with a negative 1/2. So when we do our rewrite, we're going to have a negative 1/2 integrating, and this is going to be du over 1 plus e to the u. Now I'm going to do this full substitution where I change those bounds too. So let's look at the lower bound and the upper bound. The lower bound started at x, which is 0. So if x is equal to 0, what would u be? Well, if I plug 0 into my u, I'm going to get 0. Upper bound, if x is equal to 2, which is where we started here, then u is equal to negative 2 squared, which is a negative 4. So my new bounds are going from 0 to a negative 4. And we know we can flip these because usually we think about that bigger number being on top. Hello everyone, I'm continuing the video. I had paused it and then forgot to hit record. So here's the continuation. And everything is worked out, so I'll explain what I've done. So with this one, remember we were doing U substitution and we figured out the bounds. And so we wrote our bounds in. Lower bound ended up being 0. Upper bound ended up being a -4. But we're used to seeing the upper bound being the bigger number. So we could use this property to flip the bounds so it's the way we used to seeing it, but we just have to multiply by a negative. So a negative times a negative would give us a positive there. And then now we're just going to integrate. And when we integrate this guy, we're using that formula number 84. So I'm going to pull up number 84 from my integration sheet, if I can find it. So here's my integration u minus ln of u plus e to the, 1 plus e to the u plus c. So you can see how I substituted in. There's my formula integrating this. And then we need to evaluate with the bounds. So I'm going to plug in top bound using fundamental theorem of calculus minus bottom bound. And then we're going to simplify. E to the 0 is 1, so this is really going to be the ln of 2. So I have minus ln of 2 there. Distribute that negative, which would be 4, plus ln of 1 plus e to the -4. And remember, all that's multiplied by that 1/2, which came from our u substitution up here. If we wanted a decimal approximation, this is the exact value. If we wanted the decimal approximation, we could type that in the calculator and get about 1.6625. Another type of formula we're going to see here is called a reduction formula. So with a reduction formula, it's taking our function from u to some power down to something with a lower power. So it's reducing the power on that polynomial piece. So let's look at an example. Let's say we want to integrate x cubed sine of x. Now we could do that using integration by parts. And if you do that using integration by parts, you're going to get the same answer, but let's use the formula to do that. So we're going to have number 54. So it's going to be u to the n sine of u du. So let's plug in what we know. So it's going to be negative u to the n, so in our case, negative x cubed cosine of x plus n, which is 3, times the integral of x, and we're reducing the power there, so x squared cosine x dx. Now we've got to integrate this x squared cosine x. That's where we're going to use number 52. Wait, we just used 54. Now we're going to use number 55. Here it is. Apply that formula. So when I apply that to this, I'm going to get this guy. And then now we've got to integrate this x sine of x, which is going to be number 52. And then you can see how we're going to distribute just to simplify our final answer. In this example, we're looking at integrating the square root of 3 minus 5x all over 2x. So we're trying to find a formula that matches this. So this is going to be in the form of a plus bx. So a plus bu. So let's see if we can find something. But we don't have something with a 2 in the denominator. But what if we just factor that 1/2 out? Because that's the same thing as what we started with. Now we can fit that number 19 here. Our a is going to be a positive 3, and our b is going to be a -5. So we can think about this as a 3 plus -5 times x. And then plug everything into our formula. So that factor of 1/2 is out there, and they're going to use brackets. So it's going to be 2 square root 3 minus 5x plus a times the integral of 1 over x square root 3 minus 5x dx. And then we have to figure out how are we going to integrate this. Well, to me, it looks like we could use number 17, but notice in this case, our a is going to be positive because our a is actually 3. So we're going to use that top piece there. So that square root of 3 minus 5x came from that previous formula, but we're going to add 3/2 of whatever this integral is going to be using number 17. So let's plug in the pieces. It's going to be 1 over square root of 3 ln square root 3 minus 5x minus square root of 3 all over square root of 3 minus 5x plus square root of 3. So there's our antiderivative. Sometimes we can have rational functions that are written in terms of sine and cosine. And we can use power reduce. We can use formulas from the tables to help us with that too. We just have to recognize what that u substitution is going to be. So let's look at this guy. We have sine of 2x over 2 plus cosine x. Notice the arguments are not the same. We need them to be the same so that maybe we could do a u substitution. We know that there's a double angle formula for sine of 2x. That's equal to 2 sine x cosine x. So I'm going to factor that 2 in the numerator out, and then I'm going to rewrite that as cosine x sine of x. So if we let u be cosine of x, the derivative of u is negative sine of x. So that sine x is going to get absorbed inside of du. We do need a -1, compensate with a -1 outside. And now if we were to go through our 5-step process, we could integrate. So this is in the form of u du, and all of this gets absorbed in du over 2 plus u. So if we try to match this up with one of our formulas, let's go over here. I need a u over a plus u or a plus bu. So it's going to be number 3. In this case, my a is 2 and my b is 1. We're going to plug in our a and b. And then we're just going to simplify. So that's how we can use the tables to help us integrate. Now, we could also use technology. One of my favorite pieces of technology to use is Wolfram Alpha. So I just type in Wolfram Alpha. The reason I like it, it is backed by something called Mathematica, which is a very powerful mathematics program that knows how to do algebraic computations. So let's say we want to integrate that last example. So we're going to tell it to integrate. It's going to be sine of 2x divided by 2 plus cosine x. So this is telling me what it's integrating. And it's telling me it's 4 log cosine of x plus 2 minus 2 cosine x plus a constant. Okay, but look over here. It says that the log is representing the natural log. So this is not the base 10 log. This is the ln function. Okay, and that's the exact same thing that we got before. Also notice that it dropped the parentheses. We don't need the parentheses on this one. It's not, no, oh, sorry, we don't need the absolute value. It dropped the absolute value. Cosine shifted up 2 units would always be a positive value. So it recognized that, and then it was able to drop it. And we could use Wolfram to check other things as well. Let's say we wanted to integrate this guy. We had x cubed sine of x. Just thinking about it. Now I'm going to scroll down because it's going to give you various forms. Here is the one that's fully expanded, and you can see it's the same thing that we have here. Different order, but same answers. Sometimes Wolfram will do things slightly differently than the way that we do them. Like this one, we were using a table. It will give you something that's, I think, not the same thing. Let's try it. Square root of 3 minus 5x divided by 2x. So you can see that first term is the same, but then it used a hyperbolic tangent function to integrate this, whereas we use the tables to integrate that. So it approached this in a different way. If we scroll down, you will see an alternative form. This one looks like it is algebraically equivalent to what we got using the tables.